Welcome. Let's take a look at the review packet. I'll do this probably in a series of shorter videos depending on how time constraints work for me. But I'm going to primarily be going through the odds, and the intent of this, excuse me while I'm getting focused here, the intent of this is for you probably then to go back through the even problems. You should have, if you received this packet, you should have an answer key to these. So let's just take a look at the process. In order for you to be successful in this Algebra 2 Pre-Calculus Honors course, it's probably pretty imperative that you can learn new algebra concepts quickly, just due to the nature of the course. So some of these will be new to you, and some could be review, and some might be an extension of some things you already know. So number one, solve each equation. Here we have an absolute value problem, and the key to an absolute value problem is we want to treat this absolute value as though it were just a variable all unto itself, and we want to get it alone first. I have a little bit of lag issue going on, so bear with me if my timing's off on this with my voice, but I'm going to go ahead with this. So I want to get this absolute value alone. I'm going to treat it just as though it was like 6x plus 7. So of course the first thing I would do is subtract 7, and I get 6 absolute value of 6p minus 6 equals 36. I would divide away 6. We're trying to isolate the absolute value. So if we divide both sides by 6, this is just a factor, cancels, I get absolute value 6p minus 6 equals 6. And once we have the absolute value isolated, I know, for instance, if absolute value of x equals 4, I would say x either could be 4 or negative 4. And that is what I'm going to do with this. 6p minus 6, maybe 6 and the absolute value doesn't come into play, but 6p minus 6, if it was negative 6 inside of here, the absolute value would clean it up, and of course that will make the solution 6. So now it just turns into two separate equations. So our steps are we isolate the absolute value, and then we split into two separate equations. So add 6, and I get 6p is 12. Divide by 6, I get p could be 2. Add 6, and I get 6p equals 0. So p could also be, divide both sides by 6, 0. So our solution's 0 or 2. So that should model pretty clearly what you'd be doing on problem number 2 here. We'd want to remove the 2 or subtract 2 on both sides, divide both sides by negative 2, isolate the absolute value, and then split it into two separate equations. Okay, pretty similar here, just one little difference to remember. Here, I still want to, on this inequality, I still want to get the absolute value alone. So I'm going to jump to step 2 by subtracting 5 on both sides. And I'm just going to treat this temporarily as an equal to problem. Actually, I am not. I've taught it that way, but this works well. So I'm going to keep it as a greater than. So subtract 5 both sides. 8 absolute value 10m minus 7. Greater than, subtract 5 on both sides. When I subtract 5, it stays greater than, I get 56. When I divide both sides by positive 8 to get the absolute value isolated, this still stays greater than. Note this problem. At some point, you're going to be dividing both sides by negative 1 to eliminate the negative. When you divide an inequality by a negative, the inequality sign changes. So right here I am at absolute value 10m minus 7 is greater than 7, and now I'm ready to split this into two separate what would be equations but now inequalities. And one, we just drop the absolute values. Maybe 10m minus 7 just by itself is bigger than 7. But if 10m minus 7 was negative 12, the negative 12 would turn into a positive 12. So if 10m minus 7 is less than negative 7, that's also a solution. So our second possibility is 10m minus 7 might be less than negative 7. So let's review steps. We isolate the absolute value, then we split into two inequalities, and this is sort of an opposite deal. When I change the right side of the inequality to negative, I change the sign. So let's wrap this one up and see what we get on our number line. This becomes 10m, add 7 to both sides, is greater than 7. M is greater, oh, that's wrong. Bet you saw that. Greater than, add 7 to both sides, 14, is greater than 14 tenths. Divide by positive 10, greater than stays greater than. So maybe m is greater than 7 halves. Same steps, add 7 to both sides. 10m is less than, add 7, 0. So m could be less than 0. Let's take a look at that on our number line. 7 halves, 3.5. 3.5, since I can't be 3.5, I just say I build a force field around it. Open circle means I can't really touch 3.5, but I can be bigger than. I can't really touch 0, but I can be smaller than. So on the number line, this is my solution. I just need a connector word between these. And it's either going to be and or, but I need the numbers that are bigger than 3.5. There aren't numbers that are bigger than 3.5 and at the same time smaller than 0. So I either need in order to win here, in order to land on my shaded region, I either need to land up here or down here. I can't land here and there. So my connector word here is an or. When it shades outside, it's an or. Okay, let's take a look at 5 at maybe a little quicker pace. So negative absolute value 2p plus 3. Add 9 to both sides. It stays less than or equal to. Add 9 to negative 24, and I get 15. I get negative 15. Then I need to divide both sides by this negative 1. If I divide by negative 1 on an inequality, when you multiply or divide both sides by a negative, the sign changes. So I get absolute value 2p plus 3 is greater than or equal to positive 15. And now I'm ready to split and switch. Split into two separate inequalities and switch the signs. The greater than becomes less than, greater than equal to, less than equal to, positive 15 becomes negative 15. So we solve this, 2p greater than or equal to 12, subtract 3, maybe p is bigger than or equal to 6. Or 2p less than or equal to, subtract 3, negative 15 minus 3, negative 18. Maybe p is less than or equal to, divide 2, negative 9. So p greater than or equal to, now I can touch 6 right here, and I can be bigger. I can touch negative 9. Let's see, this would be negative 10, negative 9, and I could be smaller. So again, this is an outside shading. That makes this an OR problem. Okay, very good. Let's take a look at page 2. This would probably be a really good time if you want to pause and try problem 4, try problem 6. You may want to handle it this way so you get that immediate feedback on these other problems that are very similar. Okay, simplify the expression. This one involves what I would consider the most common algebra mistake. I'm distributing 10, but I'm not really distributing 10. I'm also distributing a negative. So I don't think of 10 times 4. I don't think of before I think about the numbers, I think about the signs. Negative times positive, negative. 10 times 4, 40p. Minus times plus. Minus times plus, minus 4 times 5, 20. Minus times plus, this is a negative times a positive, negative or minus 2p. And minus times minus plus 2 times 8, 16. And now we should hopefully be home free. I've got minus 40p's and another minus 2p's. Those get along for a total of minus 42p's. and I've got a minus 20 fighting against a plus 16. That's a battle. So we subtract, we get 4, and the minuses win the battle. And that's it. As you can see, problem number 8, very, very similar. Okay, number 9. I'll see people approach these different ways, but boy, I don't dictate that you have to do things my way. If you've been doing them for a while and successful, but boy, I want you to be open-minded. I'm going to just claim that from this point forward, anytime we have compound fractions, fractions in fractions, we're just going to refer to that as a mess. And we can clean that mess in one step. You could get common denominators up here and smash these two terms together. Or on this one, get common denominators, smash them together, get common denominators in the denominator, smash them together, and then flip and multiply the fractions. But you can clean this in just one step. If you can find the least common denominator from this term, and this term, I need a factor of x minus 3, I need a factor of x, I need a factor of x minus 3, I've already got one. If you would multiply this by x minus 3 times x, the least common denominator, over x minus 3 times x, you can clean this in one step. We won't have compound fractions anymore. We'll still maybe have a little bit of algebra to do. When I take this whole package and distribute it to this term, the x minus 3 cancels the x minus 3, and I get an x times an x plus the 9. When I distribute this whole package to this term, the plain old x's cancel, and I get 9 times x minus 3. When I multiply this by this, the x minus 3's cancel, and I get 3x. Wow, that's a lot friendlier looking than what we had just a moment ago. Again, you can get common denominators, smash them together, flip and multiply, and it's going to take you 3 steps to get here. And I don't think it's any easier than this. Okay, so what do I end up with? I end up with an x squared plus 9x minus 3 over 3x. Now, I might as well talk about this and get this out of the way. One of the most common errors I ever see when we're dealing with fractions like this is we get to a point like this and we start thinking, what can I cancel? Can I cancel this x with this x? Or can I cancel this x with one of those two x factors? Well, here's the problem. This x, or this x right here, is a factor of this term, but it's not a factor of the numerator. There's not a factor of x in the numerator. If I could factor out of these 3 terms an x, I could cancel with the x. I can't cancel this 3 with this 3. This 3 is a term. This 9 is part of the term 9x. There's not a factor of 3. I can't factor out a 3 to cancel. We are done. Okay, very similar. Number 11. We've got a mess. Now, because the numerator has common denominators up here, u minus 1, maybe you want to smash those together. I'd be okay with that. But I'm going to treat it just like I treated the last one. 1, 2, 3, 4 terms. I need a factor of u minus 1. And I need a factor of u squared. So I'm going to multiply top and bottom by u squared u minus 1. Why can I do that? Didn't talk about that on the last problem. Because this is equal to 1. And this is equal to 1. I'm not changing the value, just the form. When we distribute here, the u minus 1 cancels the u minus 1, and I get 4 times u squared plus u squared times the u minus 1 cancels the u minus 1 times u squared. U squared times u squared. When I distribute this, the u minus 1 cancels, and I get 4 times u squared. Plus, when I distribute to here, the u squareds cancel, and I get 2 times u minus 1. So in the numerator, I've got a 4u squared plus a u to the fourth, all on 4u squared plus 2u minus 2. I can't directly cancel anything from up here with anything from down there because I don't have factors. Now, this could just be a thought bubble. Maybe you see we can't cancel anything, but I do see I could factor a u squared out. And I could try to factor this. I can definitely factor a 2 out. I'll do that. 2 times 2u squared plus u minus 1. And then I could try to factor this, but if I factor this, I'm going to have to match that factor. 4 plus u squared, which doesn't factor. Factors a negative 2 that I think maybe I could factor this. But I'm not going to match a factor of 4 plus u squared, and this most definitely does not factor into, here's another one I'll see, 2 plus u times 2 plus u, why not? Well, we would have to FOIL this, 4 plus 2u plus 2u, I'd need plus 4u's here before the u squared. So, although I can factor, there's no real payoff for it. This is final answer. All right, number 13, long dividing polynomials. Going to become a skill that's going to be important in your course next year, but again, if you haven't done this before, I think we're going to be in pretty good shape here. I'm going to treat it just like a long division problem. X plus 7 goes into, I've got it to the third, to the second, to the first, and then an x to the 0th here. If, let's say there was no x squared term here, I would set this up as 7x cubed, and then I would put plus 0x squared, but I don't have any holes in this polynomial. If there were no 15x's here, I would put plus 0x, plus 15x and minus 43. And now we're to long divide, and all I'm going to focus in on is this right now. X times what is 7x cubed, 7x squared. Since it's squared, I'm going to put it over my squared column. 7x squared. 7x squared times x is 7x cubed. 7x squared times 7 is plus 49x squared. Now, important to remember, when we long divide and we get to here, we are subtracting these things. So I get 0, I better, so I did it. I get 3x squareds here, and then I bring down a plus 15x. And I ask, how many times does x go into 3x squared? Plus 3x times. That gives me, of course, 3x squared plus 21x. But we are subtracting those. And I get 0, negative 6x minus 43, at which point I say, how many times does x go into negative 6x? Minus 6 times gives me negative 6x minus 42, but I am subtracting this, so this actually becomes plus and plus. And I end up with 0, negative 1. What do we do with the negative 1? Well, that negative 1 hasn't been divided by x plus 7 yet. So minus 1 needing to be divided by x plus 7. I think it'd be a really good time for you to pause the video and try number 14. Check it with your answer key that you were given. Okay, welcome back. Simplify. Now, I probably should put an extension problem to this because I didn't notice when I ran this that we have some really good things happening here. Square root of 5 plus 3 on square root of 16, but we should notice that that can be square root of 5 plus 3 all on square root of 16 is 4. And there's really nothing for us to do other than just that. And I noticed that in number 16, this radical down here is a square root of 9. Of course, that's just 3. So here's just an extra example. An extra example for you could be something like, what if I had square root of 5 plus 3 instead over square root of, let's say, square root of 20. So now, the square root of 5, there are no factors in 5 other than 5 and 1, so it is stuck in that square root for right now. 20 is either 4 times 5 or 2 times 10 or 1 times 20, but 4 times 5, 4 is a perfect square, so if I treat this like square root of 4 times square root of 5, this becomes square root of 5 plus 3 on 2 root 5, which sometimes is just fine for an answer, but at this point right here, we're going to try to rationalize denominators, and square root of 5 is an irrational number. So I think you've probably done this before. We multiply by square root of 5 on square root of 5, and we get square root of 5 times square root of 5, 5, plus square root of 5 times 3, 3 root 5, all on square root of 5 times square root of 5, 5 times 2, 10. And now, I want you just to answer this to yourself because I probably won't be able to hear you. May I reduce this 10 and this 5? The 10's ready to reduce because 5 is a factor of the bottom, but 5 is not a factor of the top. Or could I factor a 5 out of here? Of course not. This isn't a 5. This is a square root of 5. I can't factor a 5 out of there. So this would be our solution to my little extra example problem here. Okay, simplify each expression. We got a really good situation here. I think you probably all by now know when we divide fractions, we can flip and multiply, and I will do that. But take a good look at this. This is just a one-step, what I would call a V8 problem. They may still be out, V8 commercials, when somebody's drinking a soda or something like that, and they see somebody next to them drinking a V8, and they smack themselves on the head and said, wow, I could have had a V8. This is kind of one of those moments, because I can actually, and you're rarely given this opportunity, I can actually go 8b divided by 1 is 8, and b squared minus 4b minus 32 divided by b squared minus 4b minus 32 is 1. So this is just going to be 8b over 1. But our norm for doing this would be to go 8b on, let's factor this, factors of negative 32 that add up to be, and again, you wouldn't have to do that for this problem because it's a special case, but factors of negative 32 that add up to negative 4 would be negative 8 and positive 4. And then flip this factor. This is also b plus 4 times b minus 8 over 1. And then we can say, well, this top cancels this bottom, and this top cancels that bottom, and I get 8b on 1, which is, of course, 8b. So you would do something similar here. 10n is already in two factors. n minus 10, we can't factor that. We're going to change this to times, flip it, and hopefully we get some factors, because I think you're going to have some success factoring this, and it looks like we might be able to get a 1 and 10. Might be able to get an n minus 10 here, factors. So I'll leave that for you. Okay, number 19, solve by factoring. It does mean, boy, this is a biggie. I'll see people try to solve equations by getting things like x plus 2 times x minus 4 equals 6. That is useless to us, because this could be 2 and this could be 3, or this could be 3 and this could be 2, or this could be negative 6 and this could be negative 1, or this could be 12 and this could be a half. There is no magic in factoring to solve equations unless one side's 0. So rather than factor b out of these, I'm going to bring the 10 over. And I've got 7b squared plus 37b plus 10 equals 0. See, if this was x plus 2 times x minus 4 equals 0, then I know that one of those two numbers must be 0. So I need to try to factor this beast. Well, if it factors, it's going to be 7b and b. And now I got factors of 10. I need factors of 7 times 10, 70, that add up to be 37. And this will be, I know that you've probably been taught to factor this. I'm going to do this maybe a little bit differently, and then we'll be able to talk about it. I don't care so long as you can factor. Since they factor to be positive, and they have to add up to be positive, I need plus and plus, and hopefully our number sense is pretty good. Looks like 35 and 2 will do the job. And here's where you might place those numbers or put those numbers on 7. But watch this. I already knew I needed a 7 and a 1. I need an outside factor to either be 2 or 35. Well, 7 times what? There is no integer that's going to get me to 2. 7 times 5 plus 5 here. Inside factor needs to be positive 2. So this has to be plus 2b. Let's see. 7b squared plus 35b plus 2 more b's, got it, and plus 10. If that equals 0, then either 7b plus 2 is 0 or b plus 5 is 0. b would be, let's do this in one step, subtract 2 first and then divide 7. b would be just subtract 5. Okay. So not the easiest factoring problem, but one that should be within our grasp. Probably be a very good time for you to try number 20. Solve each equation with the quadratic formula. Oh, quadratic formula. Opposite of b plus or minus square root of b squared minus 4ac all over 2a. The key to this, once again, I need to have all three terms on the same side. So n squared minus 6n minus 23, subtract 23 on both sides, equals 0. A is 1, b is negative 6, c is negative 23. A quick check, could I factor it? Factors of 23, negative 23 that add up to negative 6, no chance. The only factors are 1 and 23. So the opposite of b, 6, plus or minus square root of b squared, negative 6 times negative 6, 36, minus 4 times a times 1 times a negative 23 makes this plus. All over 2a, 2 times 1, 2. So I get 6 plus or minus. No criming, don't go into calculator on this. 36 plus, let's see, we get 92 here, all on 2, use some space here, 6 plus or minus square root of 128, and now 128, wow, that's a pretty decent number. Half of 128 is 64. So I could be thinking of this as 6 plus square root of 64 times 2 all on 2, or 6 plus or minus square root of 64, 8 square root of 2 on 2. Now, can we reduce the 2 and the 6? No. Can we reduce the 2 and the 8? No, but can I reduce the top and bottom by 2? Half of 6 is 3. Half of 8 apples is 4 apples. This equals 3 plus or minus 4 apples. Okay, good time for you to try number 22. Let's take a look. Solve by completing the square. This might be a new skill for you. I'm not certain. But it becomes very, very useful in calculus and trigonometry, and especially dealing with conic sections, which is oftentimes a challenging unit because of this one skill. So here is the deal. We have a quadratic equation, and if I wanted to use quadratic formula to solve, I'd subtract 2 on this side. Okay, here's what I'm going to do. I'm going to leave my x terms on this side. 8x squared plus 16x equals, I'm going to leave a blank, well, it doesn't matter, I don't need that blank here yet. I'm going to add 40 to both sides, 42. Now, I'm going to factor 8 out of this, not because I can. I don't care what would be behind my finger there. Whatever the number is, I'm still going to factor out an 8. I have to get a lead coefficient of 1 in front of the x squared. It just so happens that this is convenient to factor out an 8. I'm going to leave a blank equals 42. Now, nobody's going to debate, I think, that this isn't exactly the same as that. If I distributed the 8, I'm right back to here. To complete the square, once we have this lead coefficient of 1, I take half of this number and square it. Half of 2, 1. 1 squared is 1, and I put plus 1 in here. Now, think about that for a second. Is this now the same equation as what we had there? I get 8x squared plus 16x plus 8 equals 42. I really just added 8 to this side. If I did that, there's no way, if these were equal, I can't add 8 to this side and keep them equal. The only way I can keep those equal is by putting plus 8 here. See, I didn't really add 1. So I get x squared plus 2x plus 1 equals, whoops, I get 8 times that. Excuse me, I don't know where I'm going here. Sorry. Let's do that again. I get 8 times, this should be a perfect square, which means we can factor it. X plus 1 squared equals 42 plus 8, 50. Now I'm going to divide by 8. X plus 1 squared equals 50 on 8, or 25 on 4. Okay, here's another common mistake I'll see people make. Let's say we had x squared equals 16, and I'd say, what is x? Probably half of you out there in YouTube land right now are saying, oh, x would be 4, but that's half right. X would be plus or minus the square root of 16. X could be negative 4. That's a little sidebar right now. X could be negative 4, because negative 4 squared is also 16. So to get rid of a squared, x plus 1 equals plus or minus square root of 25/4, which is really a nice fraction to have underneath the square root sign. So x is, see if you follow this, 5/2 plus or minus, and subtract 1 to get x alone. Subtract 1, I'm going to subtract 2 on 2. So x is either positive 5/2, minus 2/2, 3/2, or negative 5/2, minus 5/2, excuse me, negative 5/2 minus 2/2, negative 7/2. Okay. All right, so I think that's probably a new skill. Let's take a look at another one. First thing I'm going to do, I'm going to group my r's on one side. I'm going to factor out a 4. It's convenient, but I have to. Plus 2r, I'm going to leave a blank. I'm going to add 23 to both sides. When I add 23 to this side, 23 joins a negative 2, I get 21. These are equivalent equations. But I need to take, and once again, it's a really nice convenient number, not always that case. I need to take 2, divide by 2, square it. If this was a 7, I'd take 7, divide by 2, and square. 2 divided by 2, 1. 1 squared, 1. Plus 1, that did not exist. I really just added 4 here. So to keep the equations balanced, I have to add 4 there. And wow, this problem is going to end up a lot like the last one. And I get 4 times, this is r plus 1 squared. This process gives us a perfect square if we do it correctly. Equals 25. See where we're headed here? R plus 1 squared equals, divide by 4, 25/4. So r plus 1 equals plus or minus, square, again, apologize, almost the same problem, plus or minus 5/2, subtract 1, and I get R equals, very interesting that this turned out to be the same. These are all generated just randomly. I get plus or minus 5 halves. No, I think we can see why. Plus or minus 5 halves, and I have to subtract 1 or subtract 2 halves from that. So once again, R is either 5 minus 2, 3 halves, or negative 5 minus 2, negative 7 halves. Little subliminal messaging there if you saw that one. I don't know. We got a little Cubs World Series banter going on there. Okay, that is the point where I'm going to stop on this first video. Stay tuned. We'll have another one. It may already be up on the website. And good luck.